Right now, on a mountaintop in the Chilean Atacama Desert, a camera the size of a small car is taking a new photograph of the night sky roughly every 40 seconds, and it has not stopped since the 1st of July. Each of those photographs is so large that you would need hundreds of ultra-high definition television screens lined up side by side just to display a single one of them at full resolution. Every 3 nights, without exception, this machine covers the entire visible southern sky, and it will keep doing that every 3 nights for the next 10 years. In its first month and a half of preliminary testing alone, before its real mission had even formally begun, it had already found more than 11,000 asteroids nobody on Earth had ever cataloged before, including dozens close enough to be genuinely worth tracking. And that was just the warm-up. This is the story of the Vera C. Rubin Observatory, why astronomers are already using words like revolutionary and unprecedented to describe what it is doing, and why the discoveries it is producing right now in the summer of 2026 are only the very beginning of something that is about to change how humanity understands the universe. Stay with me, because by the end of this, you will understand exactly why this single telescope is expected to generate more astronomical data in its first year than every other observatory in history combined. If stories like this one are what you come here for, go ahead and subscribe now, because this particular machine is just getting started, and what it finds over the next 10 years is going to keep reshaping the headlines again and again. To understand why this observatory matters so much, you first have to understand who it is named after, because the story behind that name is not a footnote. It is the entire reason this telescope exists in the first place. Vera Rubin was an American astronomer born in Philadelphia in 1928, a woman who fell in love with the night sky as a child and who spent much of her early career being told, directly and repeatedly, that astronomy was not a field where she belonged. When she first presented her research at a meeting of the American Astronomical Society in 1950, fresh out of graduate school, she stood up and delivered a memorized 10-minute talk, and one man after another rose afterward to explain why what she had just described could not possibly be correct. She kept working anyway. In the late 1960s, working at Kitt Peak National Observatory in Arizona, alongside her collaborator Kent Ford, Rubin began measuring exactly how fast stars orbit around the centers of spiral galaxies, starting with the Andromeda Galaxy, the Milky Way's nearest large neighbor. The expectation, based on everything astronomers understood about gravity at the time, was straightforward. Stars near the outer edge of a galaxy should orbit more slowly than stars closer to the center, the same way planets farther from the sun move more slowly than planets close to it. That is not what Rubin found. The stars in the outer regions of Andromeda were orbiting just as fast as the stars near its core, so fast that by every known law of physics, the galaxy should have been flying apart. It was not flying apart. Something invisible, something with mass but no light of its own, had to be holding it together. Rubin and Ford went on to study dozens more spiral galaxies throughout the 1970s, and the pattern held every single time. By 1980, when their landmark paper charting the rotation curves of 21 separate galaxies was published in the Astrophysical Journal, the evidence had become impossible to dismiss. This invisible mass, first theorized in the 1930s by the astronomer Fritz Zwicky, and largely ignored for decades afterward because the idea seemed too outrageous to take seriously, was real, and it was everywhere. Today, scientists estimate that this substance, which we still call dark matter for lack of a better name, makes up roughly 85% of all the matter in the universe. Everything you can see with a telescope, every star, every planet, every galaxy, every glowing cloud of gas, is only a small fraction of what is actually out there. Rubin never claimed sole credit for the discovery, and she spent much of the rest of her career mentoring younger women, trying to break into a field that had once told her she did not belong in it. She died in December 2016 at the age of 88, having fundamentally changed how humanity understands what the universe is actually made of, without ever receiving the one honor most people assumed was inevitable, a Nobel Prize. In 2019, 3 years after her death, the United States Congress voted to formally rename what had been called the Large Synoptic Survey Telescope in her honor. It is a fitting choice because the machine now bearing her name was built specifically to finish the work she started, mapping the invisible architecture of the universe on a scale no single astronomer, however brilliant, could ever have managed with a spectrograph and a photographic plate. Here's the misconception most people carry about telescopes like this one: the assumption that a bigger telescope simply means a clearer, more zoomed-in picture of a single distant object. That is not what makes the Rubin Observatory revolutionary. Plenty of existing telescopes, including the James Webb Space Telescope, can stare at one tiny patch of sky for hours or days and pull out extraordinary detail from a single galaxy or a single planet's atmosphere. Rubin was built to do something almost entirely different. It was designed to look at everything, constantly, and to notice the instant anything changes. Sitting atop Cerro Pachon, a mountain roughly 2,700 meters high in one of the driest, darkest, most astronomically pristine locations on Earth, the observatory combines an 4-meter primary mirror with a camera that is, by a wide margin, the largest digital camera ever constructed. A device weighing roughly 3,000 kilograms and capturing images at 3,200 megapixels, more than 3,000 times the resolution of a typical modern smartphone camera. Because the telescope's optical design lets it capture an enormous patch of sky in a single exposure, roughly 10 square degrees at a time, equivalent to about 45 full moons side by side, it can do something no observatory before it has ever managed. It can photograph the entire visible southern sky, all of it, once every 3 to 4 nights, over and over for a full decade. It helps to understand exactly why earlier telescopes were never able to attempt something like this. Most large observatories built before Rubin were optimized for depth rather than breadth, meaning they could capture extraordinarily faint, distant light, but only from a tiny sliver of sky at a time, sometimes no larger than a fraction of the full moon in any single exposure. Mapping the entire sky with an instrument like that would take decades, even at a punishing observing pace. And by the time you finished, the earliest images would already be years out of date, useless for catching anything that changes on a human timescale. Other surveys built specifically for wide coverage, meanwhile, historically had to sacrifice sensitivity, catching only the brightest, closest, most obvious objects while missing everything faint or distant. Rubin's entire design exists to eliminate that trade-off, combining a mirror large enough to gather faint, distant light with a field of view wide enough to cover enormous stretches of sky in a single pass. Something earlier generations of telescope engineers understood was desirable, but simply did not have the optical or computing technology to actually build. That relentless repetition is the actual point, and it took more than 2 decades of planning, engineering, and construction to make it possible. The project was originally conceived in the mid-1990s under the working name of the Dark Matter Telescope, later becoming the Large Synoptic Survey Telescope, before finally being renamed for Vera Rubin in 2019. Its signature 10-year mission is called the Legacy Survey of Space and Time, LSST for short, and it formally began on July 1st, 2026, after years of testing, calibration, and a preliminary commissioning phase that had already started quietly producing results well before the official start date. Bob Blum, director of Rubin Observatory at NSF NORLab, described the beginning of that survey as a moment shaped by more than 2 decades of dedicated work from a team spread across the globe. And Phil Marshall, deputy director of Rubin operations for SLAC, described the milestone in a phrase that has now become something of an unofficial motto for the project, calling it the moment the team finally got to call action on the greatest cosmic movie ever made. That phrase is not simply marketing language. It describes with real precision what the telescope is actually doing. Every single image Rubin captures gets automatically compared against a carefully built template, a composite image assembled from everything the telescope has already photographed of that same patch of sky. Any pixel that differs between the new image and the template, a star that is brightened or dimmed, an object that has moved, a point of light that has appeared where nothing existed before, or a point of light that has simply vanished, gets flagged within seconds and turned into what the observatory calls an alert. During a single overnight test of this alert system back in February of this year, using a patch of sky the telescope had already built up enough historical data on, Rubin generated 800,000 individual alerts in one night alone. Stephen Smart, an astronomer at the University of Oxford who helps lead one of the data services responsible for sorting through this flood of information, described the scale of it plainly, noting that literally everything that changed, appeared or disappeared across that patch of sky was cataloged and triggered its own individual alert. Now that the full 10-year survey is underway, the observatory is expected to produce something on the order of 7 million alerts and roughly 20 terabytes of new data every single night, an amount of information so large that no team of human astronomers could ever manually review it. Machine learning systems built specifically for this project now do the first pass of sorting, flagging, which of those millions of nightly changes are worth a human scientist's attention, and which are simply the ordinary flickering of a universe that never actually holds still. Even before the official 10-year survey began, during a preliminary testing phase that ran for roughly 7 weeks in the spring of 2025, Rubin had already started producing results that genuinely surprised the scientists reviewing them. In that short window, using only a fraction of its eventual observing time, the telescope discovered more than 11,000 previously unknown asteroids, along with detections of more than 80,000 asteroids that had already been cataloged by earlier surveys, submitting all of it to the International Astronomical Union's Minor Planets Center for confirmation. Among the near-Earth objects in that batch were 33 asteroids nobody had ever tracked before, along with hundreds of trans-Neptunian objects drifting in the frozen outer reaches of the solar system, far beyond Neptune's orbit. To put that number in perspective, Astronomers using traditional ground-based surveys had spent roughly 2 centuries slowly building up humanity's total known catalog of asteroids. Rubin is expected to roughly double that entire 2-century catalog within its very first year of full operation, and to eventually discover somewhere in the range of 5 million new asteroids over the full course of its 10-year survey. One single object from that early batch of discoveries deserves particular attention because it set a genuine scientific record within days of being found. Catalogued as 2025 MN45, this asteroid, roughly 710 meters across, wider than most skyscrapers on Earth, turned out to be spinning on its axis once every 1.88 minutes, making it the fastest rotating asteroid of its size class ever recorded by any observatory anywhere. Alongside it, in that same small slice of preliminary data, Rubin identified 16 additional superfast rotators completing a full spin somewhere between 13 minutes and just over 2 hours, and 2 even more extreme ultrafast rotators spinning in under 2 minutes each. Nearly all of these objects live in the main asteroid belt between Mars and Jupiter, a region astronomers had assumed was already fairly well mapped after decades of prior surveys. Rubin found genuinely new, genuinely extreme physics sitting there in plain sight, simply because no previous telescope had ever been fast enough or sensitive enough to catch it. If you have found any of this as surprising as I did while researching it, drop a comment letting me know which discovery stood out most to you, because it genuinely helps shape which parts of this ongoing story are worth digging into next. The asteroid census, as impressive as it already is really only one piece of what this observatory was built to accomplish, and arguably not even the most important piece. Because sitting underneath all of this is the actual reason Rubin was funded and built in the first place. A direct continuation of the very question Vera Rubin herself spent her career trying to answer. What exactly is dark matter and what is dark energy? The even stranger, even less understood force that appears to be causing the expansion of the universe to accelerate rather than slow down. Roughly 95% of everything that exists falls into one of these 2 categories, dark matter or dark energy. And after nearly a century of study, scientists still do not know what either one actually is. Rubin's 10-year survey is specifically designed to attack this problem using a technique called weak gravitational lensing, measuring the extremely subtle way that the mass of foreground galaxies bends and distorts the light of galaxies sitting billions of light years farther behind them. A single image of a single galaxy cannot reveal much through this method, but billions of galaxies, imaged repeatedly over 10 years with the kind of precision Rubin's instruments are capable of, can begin to trace the invisible scaffolding of dark matter stretched across the cosmos, essentially completing, on a scale of the entire observable universe, the exact same kind of measurement Vera Rubin was making one galaxy at a time with a spectrograph in the 1970s. Just weeks ago, in a data release focused on a well-studied patch of sky known as the Cosmos Field, a region that has already been examined in extraordinary detail by the Hubble Space Telescope, the James Webb Space Telescope, and several X-ray and infrared observatories, Rubin released its own exceptionally deep view of that same patch, adding yet another layer to one of the most intensively studied regions of sky in the history of astronomy. Layering Rubin's data on top of everything those earlier observatories had already captured gives researchers something genuinely new, a way to cross-check faint, difficult-to-confirm objects and events against multiple independent instruments, simultaneously, dramatically increasing confidence in discoveries that might otherwise sit as ambiguous, single-telescope detections for years. Supernovae represent another category of discovery where Rubin's specific design gives it an advantage no earlier survey has had. A supernova, the explosive death of a massive star, brightens and fades over a period of days to weeks, and catching one in its earliest hours before it reaches peak brightness is enormously valuable to astronomers trying to understand the physics of how these explosions actually unfold. Because most sky surveys before Rubin could only revisit a given patch of sky every several days or weeks at best, they tended to catch supernovae partway through their evolution, missing the crucial early rise entirely. Rubin's 3 to 4 night cadence across the entire sky means it is now catching stellar explosions closer to the moment they actually begin, and its automated alert system can notify other telescopes within minutes, giving astronomers around the world a genuine chance to point larger, more specialized instruments at a fresh explosion while it is still evolving rather than studying it only after the fact. Certain rare categories of stellar explosion known as failed supernovae, where a massive star appears to simply vanish without producing the expected explosion at all, are also expected to turn up far more frequently in Rubin's data than in any previous survey, simply because catching that kind of event requires exactly the sort of dense, repeated coverage that no earlier telescope was capable of providing. There is one more category of discovery that Rubin is specifically built to catch, and it may end up being the single most talked about thing this observatory ever finds. Interstellar objects, physical pieces of material that formed around other stars entirely, that drifted across the vast emptiness between star systems for potentially billions of years, and that happened, purely by chance, to pass close enough to our own sun for us to actually detect them. As of right now, humanity has only ever confirmed 3 of these visitors. The first, a strange, elongated object called Oumuamua, was spotted in 2017. The second, a more ordinary-looking comet named Borisov, was found in 2019. The third, and by far the most extensively studied, a comet called 3I Atlas, was discovered in July of last year by a different survey network entirely. And in a striking twist, astronomers later went back through Rubin's own preliminary test data and found that the observatory had actually captured images of that same interstellar comet 10 full days before its official discovery elsewhere, sitting quietly in the data the whole time, unnoticed until someone knew exactly where to look. Scientists studying that comet in the time since have found it carries chemistry that formed somewhere unusually cold, in an environment far colder than anywhere in our own solar system's history. And its composition may date back somewhere between 10 and 12 billion years, potentially making it older than the Sun itself. That retroactive discovery inside Rubin's own early data is exactly why astronomers are now so genuinely excited about what comes next. Rosemary Dorsey, an astrophysicist at the University of Helsinki who studies interstellar objects, has been careful to point out that nobody actually knows how many more of these visitors Rubin's full 10-year survey will eventually turn up, offering a wide range of anywhere from 5 to 500, depending on how frequently these objects are actually ejected from other star systems in the first place. What is clear is that with Rubin now scanning the entire visible sky every few nights instead of relying on smaller, narrower surveys that might only catch a fraction of the sky in a given month, the odds of catching the next interstellar visitor early, while there is still enough time to redirect other telescopes and instruments toward it before it passes through and disappears again, have improved dramatically. Unlike the network that first spotted 3I Atlas, which was built primarily to hunt for asteroids that might threaten Earth and only found that comet as a byproduct of a much narrower search, Rubin's survey strategy was specifically designed from the outset to catch fast-moving objects early in their approach, across the widest possible slice of sky, night after night, for a full decade. This is a good moment to pause and ask you for something small. If the scale of what this telescope is doing is landing the way I hope it is, go ahead and hit like on this video, because the discoveries genuinely keep coming. Roughly every single night this observatory operates. Consider for a moment exactly how much has already happened in the short span since Rubin's first full images were released to the public in June of last year. The observatory's earliest test images, released under the name First Look, included a genuinely stunning 7 gigapixel photograph of star-forming clouds in the constellation Lupus, immediately demonstrating a level of combined depth and field of view that no previous single instrument had ever achieved. From there, the observatory moved through a careful, methodical commissioning process, testing and calibrating its systems throughout the back half of 2025 and into early 2026. While its alert stream, the automated system responsible for flagging changes in the sky in near real time, formally switched on in February of this year. By April, the first large batch of solar system discoveries, the 11,000 new asteroids, had already been submitted and confirmed. By July 1st, the full 10-year legacy survey of space and time was officially underway, and the observatory has not stopped collecting data since. Brian Stone, who was performing the duties of the vacant United States National Science Foundation director role at the time, described the beginning of that survey as the moment the project finally began filming the greatest cosmic movie ever made, a phrase that has since been repeated by nearly everyone connected to the project, not because it is a catchy line, but because it is, in a very real sense, an accurate description of what a decade of continuous whole-sky imaging actually produces. Over 10 years, Rubin is expected to capture detailed images of roughly 17 billion individual stars and 20 billion separate galaxies, a genuine, moving, time-lapse record of how the universe itself changes, night by night, year by year, on a scale nobody has ever attempted before. What makes all of this even more remarkable is how young this entire dataset still is. The observatory has been in full survey mode for barely more than a month as of this recording, and it has already produced a record-breaking asteroid, a retroactive interstellar comet detection, a fresh, deep-field view of one of astronomy's most studied patches of sky, and millions of nightly alerts flagging changes across the heavens that no human being had ever noticed before. Nearly every astronomer connected to this project describes the same underlying feeling when asked about it, a mixture of genuine excitement and genuine uncertainty about exactly what the coming years will reveal. Because a survey built specifically to notice everything that changes is, almost by definition, a survey built to find things nobody was specifically looking for. Christopher Stubbs, an astronomer at Harvard University involved with the project, has described Rubin's unprecedented combination of a large mirror and an extraordinarily wide field of view as turning it into a genuine discovery machine, capable of contributing to everything from tracking potentially hazardous asteroids to fundamental observational cosmology, often from the exact same nightly dataset. There's a reason this kind of discovery machine had never existed before now, and it comes down to a combination of engineering challenges that simply were not solvable with earlier technology. Building a telescope capable of capturing both an enormous area of sky and extremely faint, distant light in the same exposure required an entirely new kind of optical design, one that combines the primary and tertiary mirrors into a single, unusually shaped piece of glass, a design that took years of specialized engineering to manufacture and test. The camera itself, the largest digital camera ever built, required its own dedicated refrigeration system to keep its sensors cold enough to detect the faintest possible light, without being overwhelmed by their own internal electronic noise. And the sheer volume of data the system produces each night, 20 terabytes and climbing, required an entirely new data processing pipeline capable of running automated analysis in near real time, because no team of human scientists could ever manually review that much information before the next night's images arrived, and buried it under an even larger pile of new data. None of this happened by accident, and none of it happened quickly. The project moved from an unfunded, largely theoretical concept in the 1990s through decades of engineering studies, prototype testing, and construction to the fully operational observatory now sitting atop Cerro Pachon. 2 decades of work spread across thousands of scientists, engineers, and support staff at institutions around the world went into building a machine whose entire purpose is to notice things nobody has ever seen before, as quickly and as reliably as physically possible. That is worth sitting with for a moment, because it is easy to treat a headline about 11,000 new asteroids, or a record-breaking spin rate, as just another interesting fact scrolling past on a screen. It is actually the visible tip of one of the largest, most carefully engineered scientific instruments ever constructed, finally switched on and running exactly as designed, after more time in development than most of the astronomers now using it have spent in their careers. It is also worth understanding what happens to all of this data once it leaves the mountain, because that part of the story is almost as ambitious as the telescope itself. Rubin does not simply store its images and wait for scientists to request them one at a time. Every night, the roughly 20 terabytes of freshly captured data gets processed through automated pipelines that identify moving objects, flag brightness changes, and generate the millions of alerts mentioned earlier, all within minutes of the original exposure. Those alerts are then distributed in real time to a small number of organizations called broker services, teams of astronomers and software engineers around the world who further filter, classify, and route that flood of information to the specific research groups best equipped to follow up on any given kind of event, whether that is a supernova candidate, a newly discovered asteroid, or something nobody has a name for yet. This entire distribution system had to be built essentially from scratch, because nothing on this scale had ever needed to exist before. A single human astronomer reviewing images the traditional way, one at a time, could spend an entire career studying a smaller data set than what Rubin now produces before breakfast on an average night. There is also a broader accessibility goal built directly into the project's design that deserves mention because it changes who actually gets to participate in these discoveries. Unlike many older observatories, where observing time was a scarce, tightly rationed resource awarded only to a small number of approved research proposals, each year, Rubin's data is designed to be made broadly available to the astronomical community, allowing researchers at institutions with far smaller budgets and far less observing infrastructure to work directly with world-class data that would otherwise have been completely out of reach. Bob Bloom has described this openness as central to the observatory's mission, framing Rubin as a resource built for the entire scientific community, rather than a small circle of specialists, allowing researchers anywhere in the world to participate in genuinely cutting-edge science using a shared public dataset. And this is genuinely still the beginning. The 10-year legacy survey of space and time has been running for barely more than a month. Every single night it operates. The observatory adds another layer to its time-lapse record of the universe. Another chance to catch a supernova in the earliest hours after it explodes. Another opportunity to notice a fast-moving point of light that turns out to be humanity's 4th confirmed visitor from beyond the solar system. Another small piece of evidence chipping away at one of the deepest unsolved mysteries in all of physics, the true nature of the invisible material that Vera Rubin spent her career proving must exist, even though nobody, to this day, actually knows what it is. Somewhere in the data this telescope is collecting. Tonight, right now, while you're watching this, there is very likely something nobody on Earth has ever seen before, sitting quietly in 20 terabytes of freshly captured light, waiting for an algorithm, and eventually a human scientist, to notice it. There is something worth sitting with in the fact that a telescope built to answer a question first raised by a woman who spent decades being told her data could not possibly be right is now the most powerful discovery machine in the history of ground-based astronomy. Vera Rubin never got to see this observatory switched on. She died in 2016, 3 years before Congress voted to put her name on it, and nearly a decade before its camera captured its first calibration image. But the questions she spent her career asking, questions about what actually holds a galaxy together, about what the universe is genuinely made of underneath the small visible fraction we can see with our own eyes, are the exact questions this machine is now built to chase at a scale of billions of galaxies rather than dozens, with a decade of nightly data rather than a handful of long nights at a mountaintop observatory in Arizona. Every asteroid it finds, every supernova it catches in its opening hours, every faint gravitational distortion it measures in the light of a distant galaxy, is one more small piece of an answer she spent her life trying to reach. If you want to keep up with what this observatory finds as its survey continues, and there is genuinely no way to predict what the next update will be, subscribe now and turn on notifications, because 10 years of nightly discovery from the most powerful survey telescope ever built means there's always another story coming. Share this with someone who would find it as remarkable as you hopefully did, because a machine capable of photographing the entire night sky every 3 nights for a decade, named after a woman who spent her career fighting to prove that most of the universe is invisible, deserves a wider audience than a quiet press release buried on an observatory's website. Somewhere above the Atacama Desert tonight, the camera is still rolling, the greatest cosmic movie ever made is still being filmed one frame at a time, and nobody, not even the scientists running the telescope, knows exactly what is going to show up in tomorrow's footage.